Hi, my name is Isabel Gallegos, and I'm here with Lingwei Cheng to present how redundant are redundant encodings, blindness in the wild, and racial disparity when race is unobserved. This is joint work with Derek Ouyang, Jacob Goldin, and Daniel Ho. Racial equity assessment is critical for understanding disparate impacts of policies on protected groups. This point has been emphasized by the 2021 U.S. Executive Order 13985, which requires federal agencies to conduct racial equity assessment to reduce, eliminate, and prevent racial discrimination and inequities. However, many stakeholders often do not have access to self-reported race, which poses a key limitation in conducting racial disparity assessments. One important alternative is imputation. The current state of the art is Bayesian Improved Surname and Geocoding, or BIFSG, and Bayesian Improved First Name Surname Geocoding, or BIFSG, which combine demographic information about census geographies and names via a naive Bayes calculation. Unfortunately, this technique is subject to statistical bias that can over or underestimate the level of disparity, as well as strong independence assumptions, which are often violated in practice. We also often have much more information than just name and geolocation, particularly in healthcare and medical settings. So one question is if we can leverage richer features to improve racial imputation. But as we incorporate more and more features, each potentially correlated with race, this raises a new and important concern of redundant encodings. The textbook definition considers a set of independent features, each of which is slightly correlated with a sensitive attribute such as race. And as the size of the feature set grows, the probability that a classifier can infer the sensitive attribute increases until it approaches 1. The notion that the bigger the data, the bigger the risk of redundantly encoding race has been a prominent concern in the legal, policy, and algorithmic fairness space. But very little is known about how this operates in practice. Our work examines both questions: if race imputation improves with richer features, and how this informs our understanding of redundant encoding. We do so by using supervised machine learning to impute race for disparity assessments, and by incorporating rich features beyond name and geography. At the outset, we emphasize that race is a social construct that does not fit neatly into these conventional discrete measures. Our goal is not to reify race as a concept, but to improve the reliability of associating people with racial categories to enable disparity measurement. The way we're able to answer these research questions is by leveraging a novel dataset that is uniquely positioned to answer these questions of race imputation and redundant encodings. The America Family Cohort, or AFC dataset, contains electronic healthcare records for nearly 8 million US patients, including rural, low-income, and racial minority populations. It also contains name and residential information, self-reported race, and highly granular health information. We derive a rich set of over 1,200 features from the AFC dataset, categorized and ranked by their accessibility to researchers, from baseline features, which are the probabilistic inputs to BIFSG, to medical features, which include diagnosis and procedure codes. The target label is patient self-reported race. We use conventional BIFSG as our baseline, which is a naive Bayes calculation over demographic information about census geographies and names. For our machine learning approach, we use a random forest model. We train 6 models with our baseline model, taking only the conventional BIFSG parts as inputs. We then train 5 additional models, incrementally adding demographic, behavioral, administrative, general health, and medical features.
Now I'll go over the results. First, we compare the conventional BIFSG and ML BIFSG using AUC, AUP-ROC, and AUPRC. We decide to measure AUPRC, or the area under precision and recall curve, as it is more sensitive to the changes in the positive instances. Prior studies have shown that in cases where there is a huge class imbalance problem, models can perform similarly on AU-ROC, but yield drastically different results on AUPRC. Here we observe that the ML approach performs better than conventional BIFSG on both micro and macro levels and across the metrics. We further break down the results by racial groups to understand what is driving the performance improvement. We find that the ML approach improves upon conventional BIFSG across all racial groups, with the most significant improvement for racial minorities. Secondly, we want to understand if using richer feature sets heightens the concern for redundant encodings. We train random forest model with different subset of features. We start with baseline features and gradually add in demographic, behavioral features, and so on. The O marks show the performance of ML models using the cumulatively added feature sets, whereas the X marks show the performance of the individual feature sets. As we add in more feature sets, we observe a steady but very small increase in both micro and macro AUPRC and AUROC, as the blue and orange lines trend slightly upwards but stay relatively flat. We also observe that baseline features alone yield the best performance. The small performance boost is surprising from the perspective of redundant encodings. First, redundant encodings are less about big data than the underlying quality of the data. In this setting, name and geography appear to be the most highly relevant features. Second, we observe only modest evidence that race imputations improve as medical information is added. In contrast to textbook examples, our evidence suggests that each additional feature is not an independent signal of race. Third, this evidence does not support the claim that big data violates anti-discrimination law's anti-classification principle, as race remains measured with substantial uncertainty. Now we turn to research question 3. Can we use an ML-based approach to disaggregate broad racial categories and make more precise estimates for subgroups? The OMB 1997 revision disaggregated the Asian Pacific Islander category into Asian and Native Hawaiian and Pacific Islander categories. However, the traditional BIFSG method is limited in its ability to disaggregate the API category, as it relies on API priors provided by the census. Because we have ground truth data for Asian and NHPI categories, we're able to train machine learning models that disaggregate the API category. In this table, we look at examples of two diagnoses. NHPI are twice more likely to be diagnosed with asthma and obesity than Asian. We then compare the ground truth rate of those two diagnoses against the estimated rates by conventional BIFSG, machine learning BIFSG, and the full model with the cumulative feature sets, including up to general health information. We observed that the ML models were able to disaggregate the API category, whereas the conventional BIFSG couldn't. Both ML models produce estimates closer to ground truth compared to the conventional BIFSG, and the machine learning approach with health information included produced much closer estimates to ground truth compared to the ML approach using just the BIFSG feature. This exercise shows that we can use machine learning-based approach to substantially disaggregate and detect those dramatic disparities within the API category. Lastly, we want to understand how ML methods coupled with the use of rich feature sets perform for different racial groups. Here we show the precision and recall for each racial group at the 0.5 threshold. The size of the circle corresponds to the size of the group. The transparency of the circle represents the richness of the feature set used for modeling. For example, for Black subjects, we see the circles moving from lower left to upper right as we add in more features. This means that both precision and recall improve for Black subjects as we increase the richness of the feature. We find that the impacts on precision and recall are different for racial groups as more features are incorporated. White patients experience the smallest cumulative changes as we increase the feature set from baseline to medical. Though Hispanic subjects see very little change in recall, there's a more substantial increase in precision. These findings add important considerations regarding data quality and the trade-offs between performance metrics when we use more data to conduct racial imputation. While we have shown earlier that additional features do not substantially improve imputation overall, they can impact subgroups to substantially different degrees, particularly smaller racial minorities. In summary, it is important to highlight that ML-BIFSG can improve racial imputation and can be used to disaggregate broad racial categories. Redundant encodings are less a function of the size of the data than of specific information inputs. Lastly, expanding the feature set itself can have varying impacts on subgroup prediction performance. Thank you.